For our first session of the day, we are honored to have with us Dr. Shah, the creator of Julia programming language, the one language that combines the ease of use of Python with the speed of C, plus has been downloaded over 50 million times and is taught at universities like MIT, Berkeley, Stanford, etc. Viral is also one of the authors of Circuitscape, an open source program that borrows algorithms from electronic circuit theory for ecological conservation. Plus, he has also helped create India's national identification project that we all know as Aadhaar. Doesn't that sound amazing? And we have with him us today talking about Julia and scientific ML and how Julia condensed development times to accelerate the speed of innovation. So, let's put our hands together for Dr. Shah.
This is how you go about installing Julia. You first install this program called JuliaHub, and then it will just install multiple versions of Julia and set up your environment. So let's assume that you did that, right? And I'm going to go to a couple of these repos here. Okay. So I'm going to just start Julia. This is apologies because of the screen size and the projection, but let's try to make it as good as possible. I'm just keeping the font big so that it's easy to read, but that means it'll scroll a lot as well. So this is what happens when you start Julia, and Julia is now at version 1.10. So in 2012 we came out with 0.1, and then we've had a release roughly we've had a patch release almost every 2 or 3 months, and we've had a minor release, which is 0.1, 2, 3, 4, all the way to 1.0, and then 1.1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there have been close to 20 minor releases of Julia and one major release. And when I say minor and major, is everyone familiar with semantic versioning? So Julia came out with version 1.0 in 2018, and we have not broken backwards compatibility since then, 5 years down the line now. And we've had 10 minor releases. And the word minor is kind of a misnomer because there have been tremendous, massive improvements in Julia itself. So for example, we completely upgraded our package manager. So Julia has the kind of package manager. How many of you struggle with pip on a day-to-day basis? I mean, I'm sure nobody's raising their hands, but they're all thinking. So Julia has a built-in package manager so that you don't need pip and cargo, not cargo, sorry, that's the Rust one. What's the other ones? And the Conda, and then the Conda Forge and this and that, right? So Python ecosystem went through a lot of pain figuring out its package management, how to get binaries installed, how to get the right versions, how to get it all to play well together. In Julia, it doesn't have any of that. There's a built-in package manager called PKG, and if I press the right bracket, this, I don't know how to, okay, let me show. Like this symbol right here, the right bracket, it drops me to the package manager, and then I can just go ahead and say add, I can say, for example, add data frames. And it's just going to go online, see what all the dependencies are, what all the versions are, and it's just going to go ahead and then install it and compile it. So this is now compiling these programs. So remember, Julia is an interpreted language, but it can actually be compiled, right? And that's why it gets its performance. And so the first time you install it, Julia is going to go ahead and install all the packages and compile it. Any questions? Because I'm kind of giving a brief intro to Julia before I get into some of the AI stuff. No questions? Just feel free to interrupt me. I think it's very important we make this interactive.
Yes. One quick question. So, how about the popular Python packages that we use? Do we have equivalent ones here?
There are fairly common equivalent ones. So if you use NumPy, in Julia, it's all built in. You don't have to download anything. So I'll show a demo. I'll show some very quick features like that. If you use pandas, there's this data frames package. If you're an R user, you might be familiar with data frames. Same thing in Julia. If you're plotting packages, everything, right? It all exists. You can also call any Python package or C library from Julia without any extra hassle. So I can just go ahead and call matplotlib from Julia. I can call TensorFlow. I can call PyTorch. You can pretty much call everything in addition to the 10,000 Julia packages that are out there, that are open source Julia packages. Yeah.
But in a compiled mode, how that work? If I call a Python package from Julia, in a compiled Julia mode.
No, when you're calling Python, you get whatever the Python performance is.
Okay.
Right? Because it's a foreign language. So once you hand over, it's going to go into Python, run it, and then bring the results back into Julia. But especially with C, we have very good interop. So, but let me, before I do that, there's a question at the back here.
Yeah, I mean, I'm not able to intuitively understand why Julia is better than Python. So if you can just take a simple example of a simple computation, that why is it something that's interpretable and yet.
That's a very good question. So I'll answer both of these and the foreign function interface right away. So let me give you a very simple example, right? So I'm just going to go ahead and do 1 plus 1. Okay, so this gives you 2 as you expected, but if I do 1 plus 1.0, I get 2.0, right? The first one is an integer, second one is a floating point value. Now, one of the things you can do in Julia, which you would probably do in C, is you can go ahead and say add code native, and then I go and ask what the answer is for 1 plus 1. I have to make this a little small. Okay, so this is the assembly code that Julia produces before it runs it. So even though I'm being interactive, Julia is actually going ahead, compiling your code into native assembly code and then running that code. So as a result, for the first time when you run a program, there is a pause, a compilation pause or a JIT pause, and then it caches that output and the code output and then runs it. So it's essentially, think about it like running a C program interactively where you're just compiling it every time you change it. And this is what, so now when I go ahead and do 1 plus 1.0, you will see that the assembly code is different. Now, you don't have to be an assembly programmer to figure out what's going on, but you can see that, this code looks different from this code here, right? And let me give you what's going on here, right? So this is a convert to floating point, right? So it took this first input and converted the integer 1 to a floating point value. How do you add to floating point? If I give you an integer and a floating point, you have to convert one type to the other, then add the two, and then you get the result, correct? So I went ahead, converted them, then I did a floating point addition here, and then I have a return value. So if you look at, if you're a C programmer, right, like you'd intuitively think that any program that produces compact assembly will be high performance, right? Or if it produces pages and pages and pages of code, then it's probably going to be slow. So this is one of the reasons why Julia is fast. Now we can go into a lot of language design issues around why Julia is able to do this, right? What kind of analysis of your program Julia is able to do so that it can produce this high performance code. But instead of me talking about that right now, I would refer you to, if you go to our paper here, this would be on the research page. We actually talk about it and it's fairly readable. So if you go here, there's this paper called Julia Fresh Approach to Numerical Computing. You can just get the PDF and that will tell you a little bit about the language design. Okay, so this is all good. We have, sorry, let me see where I was. So this was the Julia project page. So I was going to show how the C integration works. That's one quick demo. So I will go C call, and I can go ahead and call the clock function in Julia. Everyone's familiar with the clock function. It just gives you the time in seconds from 1960. Okay, and then I can, the result of this is an int 32-bit integer, takes no input arguments. I have messed this up somehow. Maybe this. Oops. Every time I do this, I forget something slightly different. Okay, I will come back to this in some time, but let's go C call. Oh, this is the problem. Okay, got it. Okay. So if I run this again, I get a different value, right? So this is just the time in seconds since the epoch. Now, notice that I'm actually not calling a Julia function. I'm calling a C function from Julia without having a C compiler that is compiling anything. So Julia is very well integrated deeply at the native level with the C capabilities. All right. So hopefully this at least convinces you that maybe you don't fully understand why Julia is fast, but it's maybe it's possible to believe it at least, right? That okay, it's doing good on the assembly native code generation. Yeah.
Can I have a follow-up question?
Yeah.
So you said it's converting the code into native assembly as you run it, right? Would that cause platform compatibility issues when you run the same code across multiple systems?
Absolutely, and so you
how
can.
get around that?
So Julia will do native code generation on each platform that it runs on. So this is not an x86, right? This is an Apple Mac, which is the ARM-based system. So this is actually doing it on ARM right now. But I could go ahead on x8600, I could go ahead on a GPU and do it. And Julia will do native code generation on a GPU, on an NVIDIA GPU and generate GPU instructions.
Right, but this is the same problem where Java people try to solve it with the JVs, right? They had to create an intermediate.
So they have a virtual machine.
To
Correct.
decouple the lower platform from the
Correct.
instructions being generated. If you're native compiling it, the code might work in certain way in one system. The same thing wouldn't do on another system. You compile it, slightly different behavior.
Numerical code will tend to a slightly different behavior, but nowadays, at least if you're using IEEE 754 arithmetic, which almost everyone does,
Okay.
I don't think that is a huge challenge. I mean, like if you go, I mean, this is now probably not a right level to talk about this, but if you go and look at William Kahan's homepage, who was the original creator of the IEEE 754, he will say that if you buy this Intel CPU and use this software package, then look at this aerodynamic simulation that will give you the wrong answer. Okay, fine. But broadly speaking, I'm pretty sure that any of us will do here, you will not see a major difference. I think this stuff got sorted out in the 90s and this is no longer an issue. Where it is an issue is in half precision and lower precision floating point values that you see in machine learning. Because those standards are not well understood. Every vendor is doing their own thing. NVIDIA has its own implementation, Intel has its own, AMD has its own, and you'll see variations. And these values do not have enough precision in them. So errors can accumulate in very different ways. But in machine learning, we don't care anyways, right? Like if it is roughly kind of in the right, we don't care about precision. We care about different things in machine learning.
So we do care about precision.
Well, but if you're already in half precision,
that's a different debate.
Yeah, so that's a different story. But Julia will give you what the hardware gives you. Julia does not try to abstract away the hardware and give you the same answer. Julia and Java had a different goal in its design in that sense. Java said, I don't care, I'm going to abstract away all the hardware that is there and I'm trying to go and make it all look the same. All you care about is JVM. We do not do that. We say Julia is the right language to make the best out of your hardware, whichever one you run it on. And so that's what it will get. And we use LLVM, which is not a virtual machine, so contrary to the VM in the name. So we just code gen to LLVM and then use LLVM too.
Alright, so this is the full point where I want to get to is when I write a Julia code, I still have to test it on the target platform.
Absolutely.
I cannot just code it out and hope like Java it will work in any platform.
It usually will. If you're doing very, very weird corner case stuff, you will have a problem, but you will have that problem even in Java.
I have to practice it on the platform. I mean, that's okay,
Yeah.
but I'm just making sure that it doesn't give you that level of
Like I said, I don't think it's a challenge, but I would not stand here and make a promise. If you see the difference,
that's exactly.
So practically I don't think you'll face any challenges, but that's not a design goal.
Yeah, understood. That's all.
Yeah. See, when you build a new system, you want to use existing software, right? It says, why do I need to rewrite things that are already working, right? And there are tens of thousands of open source libraries that are already available in C and Fortran and Java that I want to reuse, and so that's the reason to do it. But when I'm writing new code, I don't want to write it in C because it takes me 10x code to write it in C than it would take in Julia. I don't want to spend my time writing and typing verbose code. At that point, I want to write a new code in Julia, but I don't want to rewrite existing code that already exists. So that's why we have a foreign function interface or this bridge.
Instead of this performance, other things are there.
There are many other things, and we can kind of go into them a little bit. So what? But I'll tell you maybe one quick one, and this is the big one in Julia. Okay, everyone's used to object-oriented programming, right? Like everyone understands object-oriented programming, and that was a big thing that we sort of, in the programming community, we moved to I would say broadly in the 90s with C++ and Java. Although C++ took a lot longer to come into its in stride. Julia is built around the idea of multiple dispatch. Is anyone familiar with multiple dispatch? Maybe you might be hearing about this. Okay. So multiple dispatch is this basically very simple idea that it is a generalization of object-oriented programming, right? In object-oriented programming, you have instantiation of a type. You have an object, and then on that object you dispatch. It's a single dispatch, right? You take the first argument of your call of your method, and then you pick which method to run, and then you go ahead with it. In multiple dispatch, you pick a method that is based on the input types of all the arguments. So for example, I can go ahead in Julia and ask, hey, which which method of a particular function are you going to run? So when I do 1 plus 1, it says I'm going to do this. If you are doing 1 plus 1.0, it's going to do something else. This is the idea of multiple dispatch, that looking at the input types of all the different arguments, it will pick what function, what method of that function to run. And this is fundamentally the key design principle that allows us to get high performance, because looking at what the programmer is intending to do, we are able to pick the most specific method available, compile it optimally, and run it. And that goes all the way down into something like just adding two numbers, right? So in most systems, like you would, like in Python, you cannot go and look at the code of how addition is being done. But in Julia, you can, because Julia as a language does not know what 1 plus 1 is. It is the Julia core library that defines what addition is of floating point numbers and what it should go ahead and do. And now if I give it a half precision floating point, if I give it a 4-bit integer, or if I give it whatever weird stuff I want to do, it will use multiple dispatch to figure it out. And of course, if it doesn't have an implementation, it will say, sorry, method error. So this is the idea of multiple dispatch is one of the big breakthroughs in the Julia language. The idea was itself available around since the 1960s or 70s in the Lisp world. But Julia, in my opinion, is the first language that actually adopted this idea at its core. And that allows it to have a tremendous amount of reuse and composability that you do not see in almost any other language of similar kind. Yes, there's a lot of reflection that is built into Julia, yeah.
That's what possibly makes it high performance at the back end, right?
So I mean, eventually there is a type analysis. So when I write this code here, I'm not telling Julia what the type is, right? So Julia has to analyze the code and do type inference and say, oh, this is what it is, and then this is what the result will be, so that I can now make assumptions and then go ahead and generate optimal code. So I think everyone's maybe getting a sense for why all of this matters, right? So now I can go ahead and build, for example, I can build arrays, right? So if you're familiar with NumPy, everyone's familiar with NumPy, right? If you're a data scientist, you have to be. And then I can go ahead and create, let's do 10 to the 7, right? So this 10 million elements. This function is a native Julia function. I just ran a Julia function 10 million times in order to create this random array. And now I can go ahead and say, I'm going to just multiply it by 2. Sorry. So, and so on and so forth, right? Or I can do a plus a and whatnot. Or I can go ahead and create matrices. And I can, so now you can kind of see the startings of how do I create a neural network library, for example, right? Well, I mean, what's at the fundamental core of a transformer? It's matrix multiplication, right? So let's say if I have, and let's go with float 32, I'll take 1,000 by 1,000. Let's just print it out as well, just for fun. And then I can go ahead and do a times a. And I don't know if you noticed, but there was a slight pause before it did that. I'm going to run it again, and there's no pause. Right? So that was the first time it JIT compiled the program. The next time, it just ran it right away. So now that you have your matrix multiplication, I can go ahead and do all sorts of stuff with it. I can go ahead and do an LU decomposition. Oops, go say linear algebra. I can go ahead and do a linear decomposition. I can go ahead and calculate its eigenvalues. I have my full linear algebra toolkit with me. Similarly, I have my entire data frame toolkit. So I can load data from a CSV file, and then I can convert it to a matrix, and then I can go ahead and do all the matrix manipulation to my heart's content. And then I can also go ahead and write simple for loops, which is something you would not do in Python or R. I can write simple for loops to iterate over this entire code base and over my arrays and do whatever elements and operations I want. So the Julia implementation of simple neural networks, you could probably roll one out over the course of an afternoon, because you have all this machinery that is just available to you. And that's what the Julia Flux package does. So if you go to, I killed it. If I go to flux.jl, so Julia packages are always having a .jl suffix. And so if you just put that at the back of the name, you will just get the first hit on Google. And so Flux is a machine learning library that allows you to, it basically is your neural network library, right? That goes ahead and does all your forward passes and backward passes for a neural network. If you want to do image analysis, if you want to do image stuff, you go to a package like metalhead.jl, which is also part of the Flux ecosystem, and it has all your standard sort of image models in it. If you want to do Llama 2, you can go ahead and do that, and then I'll do a little bit of that. So just to recap, right? We started out with the simple idea of having a programming language that is simultaneously easy and fast. For the easy parts, you saw me, I'm typing away at the REPL and doing interactive stuff. But because of Julia's JIT compiler and everything, I'm able to have high performance capabilities. So now, if I want to put together a new neural network library, I can operate at both levels. I can go ahead and write low-level code and then have it all compile and run, and then I can build these higher-level interfaces so that it's easy to work with. And that is exactly what the Julia community has gone ahead and put together. And now if I want to build a transformer, right, like it's just matmls at the end of the day, and no problem. Also, one interesting thing is GPUs. I actually have a GPU on this machine, but our metal support is a bit new. Probably we are the only ones with metal support at a programming language level outside of Apple. Julia can actually run this stuff pretty easily. So there's a Julia GPU project. Our NVIDIA support is the best. Like it's pretty comprehensive, and you can write very high performance kernels. So when Flux does neural network training on a GPU, it is actually using Julia's native GPU backend to run the code. There is no CUDA. So you do not have to learn CUDA C++ in order to write high performance GPU code. You can just write regular Julia and it will just work. Of course, if you write bad Julia code, which is not GPU friendly, then it will run poorly. So Julia does not solve the bad programmer problem. Okay. But if you want to write for the GPU, then you gotta write it in a way that is GPU in the GPU programming model, and this site will give you all that stuff. So we just started adding. I like having the Apple Metal support because everyone has a GPU on their. If you have an ARM MacBook, which increasingly many of you have. How many of you have the Apple M1, M2, M3? Right, like it's almost 30% of the room already, and I would not be surprised to see more people over time. But how many of you have an NVIDIA GPU in your laptop? Maybe 3 or 4. So that should, if it's running Linux, it should, actually it'll also work with Windows as well, I believe, but with Linux as well. But I'm personally excited about the Metal support because on my Mac, I have this, so anytime I can just fire it up and do some GPU programming and see the difference, performance difference. Maybe later on, if I have a few minutes, I might just try to fire up and see the difference, performance difference for a matrix multiplication. But let's, how are we doing on time? Maybe another 10 minutes or 5 minutes? Yeah. Okay, so let's, okay, so all this is great. And before I show a Llama demo, what I wanted to do was also talk about what are we doing, right? So at JuliaHub, so Julia is an open source project, great. It started at MIT, it's got 1 million users around the world, 10,000 packages. But one of the things we as the co-founders of Julia did is we actually founded JuliaHub, which is the company that is behind Julia. We drive a lot of the core development, although we are, at the end of the day, a small contributor to the large community. But as a business, we are focusing our efforts on bringing AI technology into modeling and simulation. So we are focusing on scientific use cases. So if you're building a SPICE circuit simulator, if you're an electrical engineer using a SPICE simulator, or if you're a control engineer who's writing the control system for a new engine or for a new aircraft or for a new electric vehicle or a new battery, we are building safety critical capabilities in Julia for writing code that will run on physical devices or help you design new chips, incorporating all these ideas that we spoke about, incorporating things like automatic differentiation and gradient descent and machine learning, but while also leveraging Julia's performance in order to build a new set of scientific modeling and simulation codes. So as a company, our focus is on science and engineering use cases, but as a community, there are people who are doing everything that's out there. So just as an example, this is, yeah, please go ahead.
Since your computation is so good in Julia, why don't you have something like Simulink, like MATLAB?
That's exactly what we're building. That is exactly when I said the control engineering solution. That is exactly what Julia Sim is. So we have a product. So we built 3 products actually. Pumas is a pharmaceutical modeling and simulation tool, applying all of these ideas in the pharmaceutical domain. Julia Sim applies all of this into the Simulink or Modelica, if you're familiar with those. So that's your engineering, right? Like, so if I'm if I want to build a gearbox, or if I want to build a model of a gearbox, or a model of a braking system, or a model of a battery, or a model of an air conditioner, it allows you to sort of create these models in code and then link them together in a GUI and then hit simulate, and it will go ahead and analyze the entire system and emit code and all that stuff. So we can talk.
When is it coming out?
JuliaSim is available in early form almost right away. So the underlying thing in JuliaSim is something called modelingtoolkit.jl. That part is open source and available right now. But the production version of that, which will solve even larger problems, even complex faster, that will be commercial. Hopefully costly, because I got to make money as well, right? Sorry?
At the end of the day, that's the whole idea.
Yeah. See, as a business for us, open source at the end of the day is fantastic and it's a community, but it does not pay the bills. But what we learned over the course of our time in this industry is that science and engineering companies are not software companies, and so they don't mind paying for software. But selling to tech companies is a waste of time, because if it's open source, they're like, how many of you pay for Python? How many of you buy Anaconda? Or your companies, not you yourselves, but right? That's an unfortunate truth. I mean, RStudio, anyone paying for RStudio here? All the R users, right? So as a company, we decided that in order to keep the Julia open source project sustainable and live and happening, we need to build applications that are actually in industries where people want to pay, where there are regulatory reasons to pay, right? Like when Boeing puts code on an aircraft, they don't want to download something from the internet. Like, they need someone's neck to choke if it doesn't work. And so in a combination of sort of having the right business model and my own personal interests, in focusing on scientific applications, as a business, we are building these simulations. So the third one is a spice simulator, like I said, that we are building right now, and that will replace all the old NG spice and so on and so forth, and allow you to do amazing optimal design. So imagine if you're an electrical engineer, you have to put transistors together to develop a new sensor. And today what they do is they sit and sort of, using their intuition, they will move some dials on a GUI and pick the kind of transistor. By the way, we think of one transistor as software engineers, but when you actually build a chip, there are like thousands of different ones to pick from. So how do you pick the right one? And today it's done by intuition, but actually we can use machine learning to automatically optimize the objective function of what you're trying to fix. Like, do I want peak performance? Do I want low power? Do I want some particular part of the algorithm? So you can actually design the hardware, not just software, right? Usually software engineers think of software design, but you can actually design hardware for specific criteria. And those are the kinds of tools we are building in Julia as a company. So that's sort of the small aside. But we can talk a little bit about do you use Simulink? What prompted you? You used to use, okay. And it's kind of old and not moving anywhere, right? So that's, yeah.
That's why when you said that you're doing all these things.
So that's exactly the direction.
And I thought it would be free to use when it comes out.
Well, so there are parts of it that are free. So you can download Modeling Toolkit and try it out, and that's free. But if you come and tell me, hey, I want to put this on a car, and I want to have this kind of code generation, this chip, right? But if you want to just play with it, yeah, sure, just go for it. Modelingtoolkit.jl. So okay, so let's do one final demo. So I'm going to so what do you do if you want to see if Julia has a generative AI solution, right? So I just took llama and I put .jl to .jl at the end. I hit Google, and I found the first thing. Okay, so this is a Julia package that is that says, okay, so why not just try it out, right? And then I had a second hit as well. So I went ahead and looked at what this person has done, and interestingly, what I liked about this one is that it's actually as a comparison between llama 2.c, llama 2.c compiled with some other compiler option, and then llama 2.jl, which is the Julia implementation. And with what looks like very little effort, they've been able to get 3 or 4x the performance out of the Julia code than the C++ code. I have no familiarity with this code base, so I don't know sort of, maybe someone will come and say, oh, you should have done this or that or whatever. But this is something that someone did, and you should take a look at it and try it out. But I just took the first one out here and I ran it. And so what do you do to run it, right? So I go ahead and say Julia -- project. So one of the things that Julia does is that it has this file called project.toml in when you create a new Julia project, you typically put a project.toml file which describes all the dependencies you have. And what this file will do is it tells Julia how to instantiate your environment so that all the dependencies are pulled in, all the right versions are pulled in, and all of that, it resolves it. So if I start Julia, if I just start Julia, it's not pulling in anything. It starts as a blank clean state. But if I start it with -- project, it will read this project.toml file in my current directory, and I can then go ahead into my package manager and say instantiate. And I had already instantiated this before, so it pretty much did nothing right now, but otherwise it would have gone ahead and downloaded all these packages. Okay, and now I can go ahead and I'm just going to follow the instructions here. Right? So I already downloaded the file, so I'm not going to have to do that live. So I say go ahead and say using llama 2. Okay, so let's say using llama 2, and then I've already downloaded these two files. So this is your these are the stories. So this is the Karpathy data set, if you're familiar with it. And then I go ahead and download the tokenizer, and then I go ahead and just load the Karpathy model here with these two things as an input, right? And I can ask it what the type of is for the model. So I get a language model with the llama 2 tokenizer here, and then I can just go ahead and run it. So I just run it by giving it, the prompting text, and then the temperature, and this is kind of what it spit out, right? So this is trained on a small model, a small set of stories. So right, so you know the whole spiel of what you train it on, and then that's kind of what you get, right? So the interesting thing is that this stuff can be done on your own laptop using open source technologies, using data sets that are available, and code that is easy to read. So if I now go into the source code out here and look at the inference code for llama 2, right? So that's pretty much, what is this, like 300 lines of code for llama 2. A lot of people at JuliaCon just wrote this, within a day, right? And this. One of the things that I spoke about Julia's GPU. Julia also has built-in multi-threading, so it can just leverage all your CPU cores if you programmed your program in a multi-threading way. And this is pretty much the entire code for llama 2. So it feels, a lot of these things feel black boxy and complex, and we don't understand them and so on. But like implementing transformers and language LLMs in Julia is fairly straightforward for inference. Training is a different beast altogether, which is all about hardware and building these large models. But inference and training this on your own data set and running it, fine-tuning it all is fairly straightforward. And I would think that all of you probably have the right background to pick up these tools. And whether it's Julia or Python, I would encourage you to kind of dive into the details and figure it out. So shall we try a new prompt here? I mean, something about we are, I showed a Julia demo at the meetup. I have no idea what this is going to do. It might be completely bizarre. Okay, so it's completely bizarre because it's trained on a bunch of random stories. So it has no idea about what Julia is. It probably thinks Julia is a woman. So maybe I'm going to say I showed a Julia programming language demo. So it's just completely bizarre because of the training set, but it does what it does what it's supposed to do. It gives you your tokens. All right. So if there's maybe a last final question, should I just wrap up?
Questions?
What? Yeah.
How different from C, Python and Julia? What is the basic difference?
So that's the whole point, right? So Python, you have to write code in C, and then make it callable from Julia. It's what we from Python. That's what we call the two-language problem. That you have to be an expert in both. How many people are experts at both? Colleges don't even teach C anymore. right? It's kind of, it's actually, if you ask me, it's getting worse because everyone's like Python, 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 everything. And don't get me wrong, Python's a fantastic programming language, it's a fantastic community. But every time you hear about a monoculture that you only must do one thing and we don't need anything else, it's a problem. So if you now have to write high performance code in Python, you then have to drop down to C. Okay, but either you have to write a lot of C, or you have to have someone write it for you, and you're back to you can't debug across language boundaries. It's painful, right? This was precisely why we started Julia. So in Julia, we don't have to necessarily do that.
So one, just one last question. So which came first, Go language or Julia?
Oh, that's a good question. I think Go came before. I think Go started, when did Go start? I think 2006. Actually, it seems like same time roughly. But they started publicly, whereas they started with a big team in 2009. We started with a very small core team. So interestingly, Julia has no big money behind it. There is no Google, there's no Microsoft, there's no Apple. And if you look at sort of the programming environment successes in the last 20 years, like you have the Java ecosystem that was corporate, you have the C# .NET ecosystem that was corporate, you have Swift from Apple, which is corporate, also another statically typed language. You have Go from Google, corporate, Rust, Mozilla, also corporate. So only things I think well, Python from 90s, and also not a compiled system. What else do we have? I think it's Julia. So Julia is completely open source out there. We have the new one that Chris Latner started, Mojo, which is kind of not really out yet, but that's actually not even open source. Yeah, as far as I can tell, from my understanding, I think he said he might open source it, but that's also corporate because it's one company, but it's not a big tech. So I think it's a rare success, and I'm proud that we did a lot of the work out of Bangalore, out of India here. We all have JuliaHub has a very large team in India that's not like a back end or a back office kind of team, but actually drives a lot of the simulation products from here. So it's been a great journey. We have a long way to go, but I hope you'll all try out Julia when you're back. Thank you.